All right, so this is the post-lab exercise for the molecular formula with the copper chloride. And so this is just some imaginary data. It doesn't have anything to do with actually our formula. But let's say we took the mass of our petri dish, which we say is 24.001 grams, and the solid before heating was 25.498 grams. Once we added the solid of unknown formula, then we had our after heating, which would be 24.836. And so at this point then we did the copper, and let's say that our mass of copper then that we isolated was 0.0061. Whoops, no, 0.425, sorry. That would be really small. Okay, so 0.0425 grams. The question then is, what is our formula? Okay, so the first thing we need to figure out then is the mass of water lost. Okay, and so that is just the difference when we dehydrate. So if we take 25.498 grams minus 24.836, we should get 0.662 grams of water. Okay, and so then if we know the grams of water there, we know the grams of copper, we should then also be able to get the mass of chlorine, which would be whatever this mass is here, which I think is 1 point, what is it? It would be 1.497, I guess, grams. Okay, so that's before heating, minus the amount of water, 0.662, minus the amount of copper, 0.425. Okay, likewise, we could do it after heating and just subtract copper. It should give us the same number. And so then the grams of chlorine that we would have would be, I did not do this math real quick. That can't be right. .41 grams of chlorine. Okay, so now we can get our molar ratios. So for copper, for water, let's do water first. Water equals 0.662 divided by 18 grams per mole. And that equals 0.0368. The mass of copper then is 0.425 times the molecular mass of copper, or atomic mass of copper, which is 63.5. So that is 0.0067 moles. And then finally, the moles of chlorine, 0.41 grams divided by 35 grams per mole equals 0.0117. Okay, so now we look at the smallest one and we take the ratios. So here we've got copper as a 1, so copper 1, we can divide that. We get chlorine of 1.7. And we get this of 5.4. Okay, so that's not really a super precise number. So what we can probably go by, so if we had to try to figure out, well, what would be the, what would be our ideal number here, try to find a whole number. You might try, I don't know, multiplying the whole thing times 3 or something like that. So you might get, I don't know, if it'd be CU1 Cl 5.1 H2O 16 or something like that, or O H2O 16 H2Os, which, you know, that's not a very attractive number. So you kind of have to go with sort of what we know about copper in this case and what oxidation states it likes, and you can round a little bit. So I'd say it's probably more likely, at least the ratio of copper we can round up, and I would probably round down here. This is a little bit right in the middle, but according to this, it's probably closer to CuCl2 5H2O. That seems to be a reasonable number. And then, you know, depending on the post lab, they may actually say, okay, if you know the oxidation states, what's most reasonable? Now, water hydration, and that can vary between compounds. There's no preferred number there. So, but anyway, you can, you know, you may have to do a little rounding in this case. It's probably not, you know, could you multiply each one times 2? So it would be, you know, Cu2, because then this would be more closer to 3, I guess. Cl3 dot 11 H2O. I mean, that might be okay. I mean, but knowing what we know about copper, having a +2 charge, having a +3 oxidation state, and chlorine having a -2 is pretty unlikely. So, you know, there is some places where we, you know, back in the day when we didn't know a lot about oxidation states, which would have been, you know, hundreds of years ago, you know, this sort of thing may be more realistic. And sometimes there are compounds we don't know really the relationships. But here with this compound, we probably have a pretty decent idea. So it's probably something closer to this. But, you know, it depends. You can talk to your instructor if this confuses you, or if you have a hunch or a number that doesn't totally make sense.